Okay, hi and welcome to some notes on solving systems by graphing, also known as Video Notes 7.1 for our book. Let's remind ourselves, let's get right into it. Let's remind ourselves what it means to be a system. For us right now, we're doing linear systems. So if I look over here at this coordinate plane, I'm going to make up an imaginary line that would represent one linear function on that graph. And we've worked a lot with those, but now we're in systems, and we know systems means more than one line. So if I'm looking at this line here, what does it mean to solve this, and what does it mean to be a solution to a system if I put another line somewhere on this graph? So I'm going to make another imaginary line, and we'll graph for real in a minute. But what does it mean to be a solution to this system? System means now two lines. What does that mean? I've got two lines on here. What's the solution? And some of the stuff that we've explored, or what kind of stands out that's obvious, is that's the solution to this system, is the intersection of those two lines. And that's what we're going to explore today. What that is, how to find it by graphing specifically is what we're going to work with today, and kind of what variants, are there always a solution? Are there infinite solutions? And we'll take a look at those. So let's get into it. Again, by definition, two or more linear equations that come together form a system of linear equations. That's what this is over here on the right. And then any ordered pair, or if you will, point, is that makes both systems true. So that means we can plug in those coordinates of that point, that intersection point right there, and we can plug them into the equation. We should find that they make true statements. Then it's a solution to that system. We'll do this part by algebraic methods. In next units. Okay, so in the next unit, we'll explore that a little bit more. So let's talk a little bit more about the graphing. At this point, you have a multitude of methods to graph these. And any one that you see fit or works for that situation is one you can use. I went ahead and outlined some of the main ones that you should be versed in at this point. Obviously, always evaluation tables do work. What do I mean by evaluation table? Well, that's where you make an X and you do your work in the middle, and you get a y or an f of x out on the side, and that makes your point. So that would be an evaluation table. That works for every function always, and I can't push that enough. But in this unit, since we're talking linears, you do have slope-intercept form that you could use by plotting the b value, right, the y-intercept, and then using the slope, rise over run, to graph points from there. You can also use the standard form of an equation, which is where you find the intercepts, right? So you can have a y-intercept and find that and graph it, and then you could also have an x-intercept. Remember, they all both have zeros for the opposite coordinate of whatever intercept you're finding, and you could graph it that way. And of course, you could graph from point-slope form, which is graphing the point that's listed in there, x1 and y1, and then using the slope again, just like you did with slope-intercept form. So you have a multitude of methods for graphing. So whatever you do, you're looking to graph these lines, however method you choose, and you're trying to find that coordinate point. Hopefully it's a nice set of integers, right? For our beginning start of this, right? Eventually it may not be, in which case graphing might not be so useful, because if it's not integers, then if it's an estimate, you wouldn't want to do it graphically. We would do it algebraically at that point. So what are the possibilities on a graph that we could have? Well, we could probably come up with this, and we've probably done some activities or seen a few systems at this point where the ones that we like to see are the ones that intersect nicely at a nice intersection point that's on a grid that has nice integers, right? And if they intersect, they have one solution, the point at which they cross, right? So if they have one solution, we like to refer to them as consistent, which means they have a solution. Let me write that a little bigger because that's hard to see. That's what consistent means. And then it's independent, meaning that it's only one solution. That's really what that breaks down to. Okay? We could also have the scenario where the lines happen to be perpendicular and they don't actually intersect, which means since there's no intersection, there would be no solution. So that would refer to this problem there, and that one would go there. So no solution, we would call that an inconsistent system. If it so happens that the two lines overlap, so they are basically the same line, which means that they intersect at an infinite number of points, basically everywhere that they exist. That means that it is consistent, that it does have a solution, right? But it depends on which values you pick, because if you pick here, it's a solution. If you pick this x value, it's a solution. Wherever you pick an x value, it happens to be a solution because it intersects at all of those. So we would like to say that that's consistent and dependent. For our quiz in our class, make sure you know those terms. There's a good chance that they're going to pop up on a multiple choice. So let's see this in action then. All right, so if we're doing this in action, I've got two equations here, two linear functions that I've got, and I can choose my method for graphing. I'm looking at both of these, and I notice they happen to be in slope-intercept form. So y equals mx plus b. Because they're both in slope-intercept form, I'm going to pull off the information I need using that form, which is the y-intercept and the slope, and then I'm going to go ahead and graph them. So for the first equation, the top one here, I'm going to pull off its y-intercept, which is going to be 0, -3, and I'm going to use that to graph my first point. From there then, I'm going to take the slope, which is always the coefficient of x. In this case, it's 2, or better said, 2 over 1, so we can see the rise over run on that. And I'm going to graph that. So let's do that now in red since we have it up and going. So I'm going to go down to -3, and then I'm going to go up to right 1 is what my rise over run is telling me. I'm going to repeat that a few times, up 2, 1, 2, over 1, because that way I can get a nice neat line. Don't forget, we can do the reverse of this. -2 over -1, or down to left 1, is equivalent, right? Two negatives make a positive. And so if I do all that and I get enough points, I can graph myself a pretty nice line for that part there. So there's the first part of my system, or the first equation. Now I'm going to switch to a different color, and then by doing that, I'm going to do the second equation here. So I'm going to do 2 now. I'm going to again pull off its information. It's in slope-intercept form, so -1 is the y-intercept, so it's a 0, -1 is the point I'm pulling off. That should be my first point that I plot. And then I'm going to find the slope. Well, since there isn't a slope, we know it's 1, or in this case, 1 over 1 is a better scenario for us to use. So I'm going to plot the point 0, -1, which is my y-intercept. I'm going to go up 1 and right 1, and I'm going to repeat that process, and hopefully right there I get an intersection point, and it's a nice neat integer. But I'm going to keep going because I want to make this a nice line, so I'm going to go ahead and repeat that pattern, and then I'm going to do the equivalent, which is -1 over -1, which would be this way. And I just want you to see that the slope, or the exactly opposite slope, produces the left movement when you're doing that rise over run. So I'm going to draw that line in nicely. And what I have is a spot that I can identify as the solution. And that's what it means to find a solution to a system graphically. And I would identify that. So the solution to this system is the point 2, 1. And there's your solution for graphing it. All right, there you go. There's your notes on how to solve a system by graphing and the various forms of graphing solutions that you can find. One, no solution, or an infinite number of solutions. All right, we'll see you in class.